Okay, so we'll be starting with the second part of Omnigent, the declarative code. The agent image as a portable contract. The first major design decision is that an agent is a data before it is a process. An agent image is a directory. So this is a agent image where we call it my agent. We have configurations, we have agent.md, skills, review, tools, Python or TypeScript, MCP, agents, researcher, config map. Config map.yaml is required. Other components are discovered by convention. This format has several desirable properties. It can inspect without starting a server. It can be achieved, hashed, uploaded, and cached. Relative file travel with the agent. Subagents can be represented recursively. The parser can remain independent of storage and networking. The same artifact can be run locally or registered remotely. Why an agent, why and directory instead of large YAML file? Small agents fit in one YAML document, large ones do not. Prompts become easier to review as Markdown. Skills need their own metadata and content. Local tools are source file. MCP declarations may contain connection specific configuration. Recursive child agent need boundaries. A directory also supports content addressing. In OMI agent, server app built-in bundles are packed in deterministic tarball. Timestamp ownership and file modes are normalized. So identical content produce identical archive bytes. This lets the server avoid version churning when a built-in agent has not actually changed. This is a distributed system benefit obtained from a packaging choice. Parsing and validations are separate. So there's a parser and a validator. The parser parses a file system tree into agent spec, and the validator checks semantic rule afterwards. Parsing answers what did the author write and how does it map to types. Is this combination supported and internally consistent? The entry point is conceptually, so there is a spec which parses the agent root, then the result is validated, and then if it is not valid, then we say invalid agent, return errors. Okay. Keeping this operation separate improves tooling. A scaffolder may parse with unresolved environment reference preserved. A validator can collect several errors in one pass. A migration tool can inspect deprecated fields before rejecting anything. The type center. The parse result in the agent spec data class in OMI agent. It is important field include. So there is agent spec, there is a spec version, name, description, LLM, interaction, tools, parameters, instructions, skills, MCP server, local tools, subagent, executor, guardrails, async enable, OS environment, terminals, timers, spawn. This object is intentionally not a ORM model. Storage has different job. The spec layer receives a path and returns plain Python data. That boundary protects portability. A local linter should not need a database, and an uploaded bundle should not require server semantic merely by being parsed. Boundary protects portability. A local linter should not need a database, okay, and an uploaded bundle should not acquire server semantic merely by being parsed. Defaults are part of contract. Defaults are not uh, defaults are not conventions. They define authority. Async defaults to true. Exposing async work tools, timers default to false, spawn default to false. No OS environment means no explicit sys OS surface in the generic tool manager. Listed subagents are an allow list. Notice the asymmetry. Reading session information can be broadly useful, while creating arbitrary child session expands authority and is often. Compatibility is visible in the parser. The parser contains several migration. Prompt is a legacy alias for instruction. Values from an older LLM block are lifted into executor. Executor type and harness are inspected early because some harness use a different tool shape. Mhm. Compatibility module translate older definition into newer spec. This is practical, but it has a cost. A parser becomes harder to reason about when it is both a schema reader and a migration engine. A useful contribution rule is compatibility branches should have an owner, a test, a removal condition, and one narrow location. Omnigent mostly follows the one narrow location rule. The next improvement would be machine readable deprecation warning and a document compatible matrix. So, designing an agent without hiding authority. Consider a small repository review agent. There's a spec version, name, description, instruction is in agents.md. There's an executor, the type is Omni agent, configuration, harness is Cloud SDK, model is Cloud Sonnet, async is true, spawn is false, timers is false, OS environment, type, caller process, CWD, sandbox, write paths, okay, allow network, false, tools, agents, specialist, okay. This definition makes four decision independently. Behavior, agents.md. Execution, the Cloud SDK harness and a preferred model. Authority read oriented OS access, no network, no arbitrary spawning, composition, one name child agent. Okay, that separation is more important than the spec YAML syntax. 5.1 Harness and model are separate dimensions. A harness is not a model. Cloud Code may be routed through different credential or gateway. An OpenAI compatible gateway may serve a model for from another provider. A child agent may use a different harness for from its parent. Mhm. Okay, that's interesting. So harness is not a model. Cloud Code may be routed through different credentials or gateway. A OpenAI compatible gateway may serve a model from another provider. A child agent may use a different harness from its parent. If harness and model are collapsed into one enum, model routing becomes brittle. Omnigent stores them separately and builds provider specific environment at launch. Instructions and skills have different loading behavior. Instructions are always part of agent's behavioral context. Skills are named instruction bundle loaded when relevant. This distinction limits prompt growth. A large agent can advertise many capabilities without injecting every procedure into every turn. Bundled skills and host scope skills are also separate. The source support a skill filter for host discover skill. While treating bundle skill as a part of agent image, that difference reflect provenance. Bundle skills are authored with agent. Host skills come from machine on which it runs. Okay. Tool describe effectful capability. OMI agents support different tool origins. Built-in platform tools, local Python or TypeScript tools, MCP server, client-specific tools, OS environment tools, terminal tools, sub-agent session tools, policy management tools. These tools do not all execute in the same process. The declaration is therefore only half of the contract. The runtime must decide where each call is dissipated. Sub-agents are capabilities, not ambient globals. The new agent image spec uses tools.agent as an allow list. A child must both exist under agent and be named in the parents list. This provides discoverability, a fine tool schema, isolation between child definition, a place to validate missing references, a natural security boundary. The spec deliberately avoids wildcard inheritance in version 1. That makes composition more verbose, but it prevents accidental capability leakage. Executing one turn. The event contract. Interchangeable harness require a common vocabulary for what happens during a turn. In OMI inner executor, an executor yields event, text chunking, reason chunking, tool call request, turn complete, turn cancel, executor error. The session layer can also produce tool call complete. This is a stronger abstraction than return a string. It separates what happened from how a provider encoded it. Why events instead of one responsible object? An agent turn is a temporary process. Okay. Text delta. Okay. Tool request, tool result, reasoning maker, text delta. Okay. Completion with users. Flattening this into one response loses interactivity. Exposing provider native events leak harness specific schematic to every client. The common event model gives frontend a stable stream while permitting each harness adapter to translate. Capability method prevents false uniformity. The executor based class includes methods such as um, system does not force every harness into identical behavior. It standardizes observable schematic and asks each implementation to report the control feature it can actually support. Tool calls from a suspended point. For a harness that delegates tool execution, the sequence is harness, it action required, runner, turn awaits, then it executes the tool, output or error, tool result, and turn resumes again, more event for completion. Hmm. Dispatch tool locally. In OMI or tool dispatch makes the assumption explicit. It excludes the tool, then posts a tool result event to the session keyed harness endpoint. The call ID is the correlation key. At most one harness turn is active for a session. So the endpoint is session scoped and the call ID identifies the parked tool request within that turn. Tool dispatch is a routing table. Execute tool in OMI agent routes by tool family. If MCP manager is not none, then the output is MCP manager call tool. Okay. In if we have that, then we'll just execute. If it is in terminal tools, then we terminal execute. If there are sub agents, then we sub agent execute. If there's a timer tool, then okay. The real impact has more branches, but the architectural point is visible. The runner is the execution locality for host resources. While some MCP calls are sent through the server, so policy can be enforced centrally. Registration and execution are separate. Tool Manager in OMI Tool Manager builds the advertised tool surface from the spec. Skills configured built-in, named subagent, agent management tools, OS environment tools, terminals, local tools, client tools, asynchronous inbox tools, timers, task lifeline, commands, and policies. Registration answers may the model ask for the tool. Dispatches answer where and how the call executed. Hmm. Conflicting the two would make authorization difficult. A tool might exist in the binary but be absent in particular agent schema. Process isolation between session and harness. For embedded SDK, running everything in one process looks attractive. It avoids serialization and process startup. It also creates shared failure and shared configuration problems. Omnigent's harness process manager uses a process convention harness subprocess connected over a Unix domain socket. Why one harness process per conversation? Per conversation process provides isolation of the SDK state, independent credential and model environment, simpler cancellation and cleanup, no accidental cross session memory, a natural boundary for harness crash, compatibility with harness that expects a single native session. The cost is process startup, memory, life cycle complexity. Lazy startup amortizes the cost. Get client starts a process only when the session needs it. The resulting HTTP client is cached. The process binds a Unix socket inside an instance specific temporary directory. HTTP is used as the local protocol, but there is no TCP exposure. HTTPX requires a syntactically valid base URL, so the code uses a dummy host while sending traffic over the socket. This is useful retain family HTTP semantics while using a local transport. The configuration is fixed at process creation. The harness type and model are effectively process configuration. If either changes, the process manager respawns the harness. This is more expensive than an in-process settler, but avoids ambiguous mixed state. A resumed session would not accidentally continue on the old harness because a crashed process outlived a configuration change. Spawn logs protect a single writer invariant. Two concurrent requests can discover the same missing process without coordinating. Both might bind the same socket or launch duplicate harness. The manager uses a packet conversion log. Mm. Get spawn log, async with log, get the conversation ID. The log object is intentionally retained even after a session is released. Removing it could let an odd caller hold one lock while a new caller gets a different lock for the same conversation. Keeping lock identity preserves serialization. This is a kind of small concurrency invariant that deserves its long source comment. Parent that and orphan cleanup. Child process can outlive a crashed parent unless explicitly managed. Omnigent addresses this in several layers. The runner receives parent ID. A watchdog request shutdown when the parent disappears. Linux can set up parental death signal. Startup sweeps orphaned instance directory. And ideal reaper cleans unless harness processes. The lesson is general. Starting a subprocess is easy. Providing it cannot leak is the real feature. The distributed session. Server, host, runners, and harness. Local execution can observe Omnigen's distributed design because all components may run on one laptop. Logically, there are four layers. There's a client, there's a server, which durable states auth policy, there's a host daemon, which machine registration life, uh, runner life cycle, runner workspace, tools, terminals, harness routing, harness process, agent loop, model protocol, file system, shell, tmux, and then there's a model provider. The server owns shared truth. The server accepts agent bundle, stores session and conversation item, applies permission, exposes API, and serves interface. The public dataset guide recommends PostgreSQL for production and requires it for multiple server instances. SQLite remains suitable for simpler deployment because both the use schema they use because use the same schema and migration. Okay, the server should know that a session exists, who may access it, and what durable events occurred. It should not directly access the user's laptop file system. The host daemon represents a machine. OMI host connects a machine to server. The host tunnel, tunnels carries control frames, not arbitrary proxy HTTP traffic. Okay. The frame schema in OMI agent host frames includes hello and capacity reporting, launch stop runner, run exited notification, file system stat and directory listing, worker creation and removal. The host launches runners, but runners cannot connect okay, but runners connect to the server with their own tunnel. This keeps host control and runs data protocol partition. That separation reduces protocol coupling. A host does not need to decouple every runner request. The runner owns local resources. The runner lives when the work happens. It resolves the selected agent spec, the workspace, file system, and tools and shell tools. Terminal resources, harness produce configuration, MCP, external locality, sub agent session, asynchronous inbox. When a server is remote is and a runner is on the laptop, the server coordinates a session without receiving ambient file system access. The harness owns the agent loop. Harness process speaks to the loop's native language. It converts a omniscient message event to SDK or CLI operation approximate for appropriate for cloud agents or any other agent. It emits common event back to the runner. Simplified flow is user gives a message to the server, okay, authorize and evaluate input policy, forwards the session event to the runner. The runner message event over local HTTP and model gets the request, then the stream text and so on and so forth. Okay. If the model calls a host local tool, The runner executes it and returns the result to the harness before the harness resumes. If a policy asks, if the policy return asks, the turn parks until the user resolves the allegation. Why not let the server execute everything? A server centric design is simpler until users want to work in local repository with local credential and interactive terminal. Moving all execution to the server would require uploading source, copying credential, or mounting remote file system. It would also make a personal laptop and cloud sandbox look artificially similar. The server host runner split acknowledgements that coordinate and execution have different locality requirements. I think I'll just stop it, pause, and that will be all ending the stream.